Okay, let's talk about chapter 4. So we're going to talk about the Earth, Moon, and the sky here. Talk about some of the things we've already discussed. Um, the seasons, keeping time, the calendar, phase of the moon, oceans, tides, and then eclipses again. Okay, so you read through here, there's a couple terms here. Great circle and meridian. Make sure you know what those are. Those are just references. Remember that Greenwich, England is where the prime meridian, which is longitude. So that would be the prime meridian there, which is a half of a great circle from the North Pole down to the South Pole along the surface of the sphere. Another great circle is there, goes all the way around. But the prime meridian is defined to be where 0 degrees is, and then you can move around from that around the Earth by coordinate systems. So here's a picture of that line, special line on the planet, and it connects the North Pole to the South Pole along the surface there. Okay, so in order to locate places on Earth like Washington, D.C., you need 2 coordinates, latitude and longitude. There they are, 38 degrees north, which means you go 38 degrees above the equator and 77 degrees west of the prime meridian. And with those 2 coordinates, you can get anywhere on Earth. We have similar things on the sky, which is declination and right ascension. Okay, and right ascension is like longitude, but instead of Greenwich, the arbitrarily chosen point where we start counting is the vernal equinox, which is where the sun crosses the celestial equator. So right ascension is usually in units of time, which is hours, minutes, and seconds, but it can also be in degrees. But usually each one is 24 hours. Okay. Let's see, blah, blah, blah. So yeah, read about this, learn about the celestial sphere. So the Earth rotates. Because it rotates, this pendulum, you can see these little guys here are knocked down. And as the Earth rotates underneath this pendulum, this giant tick-tock thing going back and forth, it's going to eventually knock down all the pins. And so that's because the Earth is rotating and we're a giant ball. Okay, so the seasons. We experience seasons because the Earth is tilted either towards the sun, so we experience more heat, or it's tilted away from the sun, so we experience less heat. But there's 2 periods here where the Earth is tilted this way, which means it is not tilted towards the Earth or away from the Earth. It's kind of tilted perpendicular to the Earth. And when that's the case, we have the equinoxes, which are when there's equal amounts of light and dark on the entire planet. So 12 hours a night, 12 hours a day. And there you go. There's your 2 pictures. This is summer, more watts per meter squared. This is winter, less watts per meter squared. And so you end up with less energy hitting the ground in the winter. And so that's why the Earth gets a little bit colder then. It just gets a little bit less direct sunlight. Then this picture here, we've got the Earth, we've got the North Celestial Pole here, the North Celestial Pole and the South Celestial Pole. If you're standing here, your zenith would be there. There'd be the equator of the Earth, okay? And you can see that throughout the year, the sun will make a path high on the sky in June, and it'll make a path low on the sky in December, which is over here in this picture. So the sun changes how high it is in the sky as the year goes around, and it'll orbit and go down to December and then come back up. And so when it's higher on the sky, it lasts in the sky longer, you get more sun. Okay, so there's some special places on the latitude and longitude of the Earth, mostly the latitudes here. The Arctic Circle, above the Arctic Circle, that's, if you live up here, you'll either have all sun or all night at certain points of the year. In the Antarctic Circle, if you're below that, again, you'll have either perpetual day or perpetual night for 30 days in a row or so or longer. And what's happening is the sun's going around. It appears to just orbit around the horizon or just never rise or set. So again, take a flashlight out and a grapefruit, if you eat grapefruits, and play around with the shadows and try to imagine, put a Lego figurine on one of them or something and see how much sunlight they get as they rotates. Okay, There you go, seasonal variations. You can work through those problems. Okay, so keep in time, the length of the day is 24 hours. You can see when the Earth goes around, it rotates once, and it's rotating clockwise, so counterclockwise, so I should draw that. Well, this is, yeah, okay, so Earth is rotating around, whoop, like that. That's 24 hours. But then while it's rotating around, it's actually moving forward around the sun. So it's going to make kind of a pattern like this if you plot the location of one person on it. So there's a little bit of a change here day to day, which is why the stars back here, as you move this way, the location of the stars appear to turn as we go around. We see the stars moving further and further down. Okay, so the difference here is the sidereal day and the solar day. So a sidereal day is the day with respect to the stars, how long it takes to rotate back and face the star in the same part of the sky. And the solar day is the time it takes to face the sun again. And so one of these is 24 hours, one of them is 23 hours and 56 minutes. So stars rise 4 minutes earlier each day. Okay. And then we've got apparent solar time and mean solar time, and you can read through those, and it's just some more definitions. Okay, the international date line is this weird line here, and this is so that, you know, as you fly east, you start going forward in time, and then if you keep going, you'd end up going into the next day, but instead, boop, you just start over the day again. So that's what the international date line is to set the day and time. Okay, so the calendar here, early calendar, so we try to use the location of the sun, and if the sun's over here, for example, the light will shine through Stonehenge between two of these bricks and might cast a shadow somewhere or whatever. I don't really know how Stonehenge works, but that's kind of the idea. Keeps track of the sun and the moon, and you can sort of watch what's happening. A bunch of folks, Mayans and Incans and other folks, this is the Chichen Itza, the pyramids, the Egyptians, they all use the sun, and they notice that there are these patterns that the sun would make, and so tried to keep track of the year with different rituals and structures and things. Okay, so the Western calendar comes from the Julian calendar, okay, and so that's the time it takes for the Earth to go around the sun once. That's 365 days, about, and they just made it easy and just said, hey, 365 days, that's it. And then we've got this leap year in there, which every now and then brings it to 366 days, makes it the average length of the year, 365.25 days. Okay, so the Gregorian calendar, some interesting history here. You can read about this. It's just kind of cool. Okay, phases and motions of the moon. So you got the lunar phases, and just make sure you know all these. So it all has to do with where the sun is as the moon goes around the Earth. It takes 30 days for the moon to go around the Earth. And when it's between the sun and the Earth, then we see only the dark side, or we see the moon in shadow. We don't see the bright side of the moon because it's not facing us. But as it goes around, now we can see, and so how it appears to us is up here, this little crescent shape. So just to help explain what this figure is showing, it's showing where the moon really is along here, and then these guys are what we see, what it looks like around Earth. Okay, so make sure you know all these different phases. You know, as we're waxing to a full moon, and then we wane down to a new moon, and we go through the crescent, quarter, gibbous phase, and the gibbous, quarter, crescent phase, either waxing or waning. Okay, so learn all those. The moon is rotating around its axis as it rotates around the Earth, okay, which is cool. And it's doing this, and what this is showing you here is that if you were standing here and the moon went around and it didn't rotate, then you would always be, facing that part of the sky. You would never face another part of the sky. But the moon does not just sit still. It actually spins around as it goes around the Earth, and that means, so if you're standing here, okay, and as the moon goes around, you're always going to end up facing the Earth. Okay, so that's kind of a nice feature. If you do make a moon base, you'd always be able to have your satellites pointed at Earth, and you'd never be out of contact. Of course, if we did establish a moon base and the moon did not do that, we would set up some sort of relay station, and then it wouldn't be a big deal. Okay, so yeah, we put up some satellites around a network, a constellation of satellites. So no matter where you were on the moon, you could send up your signal, and they would beam around and then beam them to a satellite on Earth, and then you'd be fine. Okay, ocean tides and the moon. So the moon pulls on the Earth, and the Earth pulls on the moon, and this interaction causes the Earth to kind of bulge out a little bit, and I'm exaggerating it there, but when it does that, it pushes the Earth around, and the water that's on it starts flowing around into different spots, and these are called the tides when the water changes level. So the tides are caused by the Earth getting pulled and pushed, not from the moon pulling, strictly on the water, but also on the Earth itself. Okay, so it causes the oceans to lift up and push water inland and all this stuff. So you can see high tide and low tides here, ship in the water, ship on land. You might walk there and go, who puts their boats on the land? Boats belong in water. Well, if you weren't from that area, you might not realize the tides would come in. Okay, so the tides come in twice a day. So let's say you're standing here on the Earth, and you know that Earth, if you just stay put, a fourth of a day later, 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 you're going to, it takes 24 hours to go around. So if the sun's here and the moon is here on a given day, right, then you're going to sweep through, boop, 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 1, 2, 3, 4 different high and low tides. And there's differences in strengths. So if the sun is here and the moon is there, so you got the sun and the moon and they're on opposite sides like this versus 90 degrees. So you're going to have way stronger tides called spring tides when the sun and the moon are in a line versus neap tides when the sun and the moon are at 90-degree angles. Okay, so, and you can see that this picture is trying to show you that the depth of the water here is higher versus there and here. And so that's what that's all about, is by thinking about the, as the moon goes around the sun, right, you're going to have different tide strengths. And there's calendars of the tides, and you can see how the moon, over the month, the tides change quite a bit. Oh, excuse me, I'm yawning. That's embarrassing. I shouldn't yawn. Okay, eclipses of the sun and the moon. So here's your sun, there's the moon, you've got the umbra, okay, and there's this kind of area here. So the sun, the moon will block out some of the light, and as it moves across the sun, there's a couple different types of eclipses you can have. A total eclipse, you can have a partial eclipse, another partial eclipse, or a annular eclipse where the sun just kind of pops out and leaves a little bit of a mark there. Okay, let's see. Yep, so the sun here casts a shadow on the moon, and what it does on the Earth, this shadow that the moon casts onto Earth is very small, which is why it doesn't really affect the whole planet at the same time. There's a nice picture of the corona of the sun, the atmosphere. Okay, but if the moon, as it goes around, takes 30 days to go around the Earth, every month there's a chance that we could have a lunar eclipse or a solar eclipse. The chances are low because of the tilts of the orbits. But occasionally the moon will pass through the Earth's shadow instead. Now the Earth is a lot bigger than the moon, and so it casts a lot larger shadow, and so that makes it easier to see, and everybody on Earth gets to see a full moon. Okay, so solar eclipses, this is the one from 2017. So if you were in Iowa City or somewhere in the Midwest, you probably had a good shot at seeing some of the eclipse. It might not have been the full eclipse. Right along that line is the spot where you would have seen the full eclipse. Okay, and that's the end. Let's see, so summaries, learn all these key terms, yada yada. So let's just look at this. So make sure you know how to label the sky with the right ascension and declination. Make sure you know what causes the seasons and the solstices and the equinoxes. Make sure you know how to, you don't have to know either of this, but just kind of know the sidereal time and the solar day. Those are different, slightly different measurements of a day. And then the calendar, so we use the Julian calendar, well, the Gregorian calendar is kind of a shift to that. And then we've got the phases of the moon. Make sure you know those. Make sure you know the differences in the tides. Make sure you know the eclipses of the sun and the moon and what causes them. And you go through these exercises, review questions, and that helps you kind of make sure you know what's going on. You could do these if you're bored. Okay, bye.